in the past, when we first started out calculus, I would give you something like this: y equals x to the power of 3, and then I would ask you to differentiate it. So when you differentiate it, in the past, I would always say, take my word for it, that when you differentiate this, you always take the 3 down, and then the index itself gets minus by 1. I've always asked you to just accept it, but you don't fully understand why that's the case. And then several videos later, we've shown that even in the case of this being a fraction, let's say a half, it will still work. When you differentiate this gets so dy by dx here. We've shown that even in the case of it being a fraction, where you can still follow the same process. This thing here gets minus by 1, so it becomes minus a half. And even in the case of it being a negative number, it will still work. So even in the case of, let's say this here, so dy by dx equals, even in the case of it being a negative number, it will still work. Now, what we haven't seen is what happens in the case of, let's say, x to the power of something that cannot be expressed as a fraction. Let's say pi. We haven't seen in the case of it being an irrational number here. Okay, so you see, by using logs, you can actually see why it will still work in the case of it being, let's say, pi. In the case of it being an irrational number. Let's look at a case, or let's make it even more complicated. Let's look at a case of y equals x to the power of minus pi. So so let's look at it being a complicated to the power of minus pi. So you see, by you using logs, you can actually see why this will still work. So when you differentiate this, it will give you dy by dx. Well, you take this down. Take my word for it for the time being. That when you differentiate this, it will give you this, and then this index itself gets minus by 1. Okay, but you see, in the past you would just do this without really understanding out why this works. By you using logs, you can actually see that why this works. Okay, let's just do it. So now starting with this here, natural log both sides. So natural log this, and then natural log this. Okay. Now, looking at this here, you got to take the natural log of this. Well, if you look at this here, you can imagine this as being 1 over x to the power of pi. Okay, so from our knowledge of indices, whenever you have to the power of minus, we don't really understand what it means, so we jump to 1 over x to the power of whatever. So this here is the same as this here. Okay, so rewrite this as this, and remember, nothing really breaks down here, because if you look at the graph of the natural log of x here, it breaks down when you're in the negative realm. But even though pi is negative, this whole thing collectively is never a negative, because when you jump to 1 over x to the power of pi here, it cannot be a negative. This thing here cannot be a negative. Yeah, so even though pi is a negative, remember, natural log of x breaks down when you're in the negative realm. But then this thing here collectively is not a negative, so it's okay. So nothing really breaks down. Well, anyway, visualize this thing here as 1 over x to the power of pi. Okay, and then using one of the laws on logs, well, when you have one thing divided by another, that's the same as you saying log of one thing taking away the log of the other. Okay, so this thing here becomes this thing here. Okay, so now hang on. So now tidy this thing up. So using one of the laws on the power laws of log, you can actually move this down here. So that becomes this times this. Okay, so what you have at the moment is this bubble here, and what you have here is really one thing here times another. And remember that this is just a constant, it doesn't change. This here is just a constant, it doesn't change. This here is well, it changes. This thing here changes. This log 1 here is a constant. This is not a constant. Bear that in mind, okay? So that would take us to this stage here. Now use implicit differentiation now. So differentiate this. This will then give you this. And remember, y is a function of x, so it gives you dy by dx here. Differentiate this with respect to x will give you 0, because this here is just a number, okay? And then differentiate this here. It will then give you this. So this here disappears, and this here gets multiplied to the top, okay? So hang on, that will then give you this. Now to get dy by dx on its own, times both sides by y. So that will then give you this here. And remember y here is x to the power of minus pi. So let's put this thing here into this y here. So that will then give you this, and then this here gets multiplied to the top. Okay, so that will then give you this, and then yeah, so that will then give you this here, and then you can see that, well, same base here, same base here. So imagine this thing as being x to the power of 1. So that's really you getting this, taking away 1. You see, at this stage here, you can see why this thing here always gets minus by 1, because you would imagine this as to be okay. Looking at this here, we can visualize it as this. We can visualize it as pi. Hang on. We can visualize it as this: minus pi times x minus pi over x. Don't forget, this thing here will get to multiply to the top. So, well, and then imagine this to be 1. So when you simplify this, because this has the same base as this, you can just get this, take away 1. Well, you can. The reason why, well, it takes, yeah. So this thing here gets minus by y. By 1 here. This thing here gets minus by 1. I hope you can see that. You see, by you using logarithms, you can actually see why, even in a complicated case of x to the power of, let's say, minus pi, it will still work. It will be this thing take away 1. It will. Following on from the previous video, I've shown you how you can use logarithmic differentiation to see why, when you differentiate this here, this thing here gets minus by 1. Even in the case of x to the power of minus pi, it still gets minus by 1. But there's something that I want you to be aware of, in that when you try and use logarithmic differentiation, you can only use natural log. Don't use log, because when you, okay, so starting from this stage here, if you natural log both sides, you would get this. Okay, and now you would use implicit differentiation. You see, when you're here, if you differentiate this, it would be 1 over y times dy by dx. Now, if you use log, you cannot differentiate this. It won't give you this nice 1 over y thing. You see, when you differentiate the natural log of y, it will give you 1 over y. But if you use log of y, you can't. When you differentiate it to give you 1 over y, it only works with the natural log. That's the beauty of it being the natural log. We created something to be simple so that we can differentiate it. So if you use log, even though you can log equally to both sides, you can't later on differentiate it. You can't. You see, you can only differentiate it when it's a natural log. That's why we created this natural log thing, so that we can easily differentiate it. With any log, it will be too difficult to differentiate. So when you do this here, take the natural log. Don't take the normal log. Okay, so take the natural log, then you can differentiate it. Okay, bear that in mind. Okay.